We've seen that in quantum mechanics we can only make probabilistic predictions about where particles will be, and not absolute predictions, and that the degree to which we can make a prediction is constrained by the uncertainty principle. Now we turn to the tools we need to calculate these probabilities. We calculate the probabilities using something called a probability amplitude. So at any point in space and time, if we want to know the probability that a particle is there, we have to start with a two-component number, the two components being a real part plus an imaginary part, and this is the probability amplitude. The actual probability is given by the square of this, which of course gives us a real number as a probability amplitude should be, as a probability rather should be. Probability amplitudes in quantum mechanics behave rather like probabilities in regular statistics theory. So for example, if we want the probability of two sequential events in classical probability theory, we multiply the probability for the first event times the probability for the second event. Similarly, in quantum mechanics, if we want the probability amplitude for event 1 followed by event 2, we multiply the probability amplitude for event 1 times the probability amplitude for event 2. In classical mechanics, if there is a probability of an event happening one way, let's say going from A to B via path 1, this could be slit 1 in the diffraction pattern experiment, or via path 2, this could be slit 2 in that experiment. And then we would add those probabilities in classical theory, and in quantum mechanics we add the corresponding probability amplitudes. Remember again though that we are going to square the result to find the actual probability, and you can see right away that given that these numbers are complex, there is a possibility for interference when we add two complex numbers and square them. So, a summary here. In classical mechanics, we would just add the probabilities for two paths. In quantum mechanics, we will add the probability amplitudes and then square to find the probability. I've talked about probabilities for specific events at specific points. However, we in general want to know the probability of, let's say, finding an electron anywhere in space. This means that we want to know the probability amplitude. Let's just imagine a two-dimensional space now. And at any point on this diagram, we would like to know what the probability amplitude is. So we need a function that contains a list of complex numbers for all possible points in space. This function is called the wave function. It is a list of probability amplitudes for every position in space, and if these are changing with time, for every time. So the wave function then will be the tool that we will use to calculate probabilities in quantum mechanics, and we will use an equation to determine a wave function for a particular potential that a particle finds itself in, and this is the Schrödinger equation. Very often the potential is not changing as a function of time. The wave function is everywhere constant throughout space. When this happens, we refer to the wave function as stationary, and it's purely a function of position. The wave function has an important probability. If we calculate a wave function for an electron and we square it to find a probability, then the integral of the square of the wave function over all space must be 1. Why? Because there must be a probability of finding the electron somewhere in space. Notice how we've written out this square. We haven't just written psi squared. We've written this out as the complex conjugate of psi times psi, and this is how we've written the square of the wave function. We've done this because, of course, remember, psi is a list of complex numbers, and when you square a complex number, you do this by multiplying it by its complex conjugate. And of course, this integral then is 1. One final piece of useful notation we'll introduce is we'll use integrals like this all the time. And it gets a little tedious writing out the integral. So a complete equivalent to this integral, introduced by Dirac, is to abbreviate it this way. So a wave function written this way around means a complex conjugate. Written this way around means the wave function not complex conjugate. The two of them occurring together, enclosed in brackets like this, means carry out the integral. This left bracket's called a bra, this right bracket a ket. So a bracketed pair of wave functions means complete the integral, and then, as you saw above, the result of doing that is just to give a unit probability. Finally, we need to consider what happens to wave functions when we have more than one particle. And this turns out to be quite a subtle point in quantum mechanics, and we'll deal with it in the next unit. Before we do that, though, let me just introduce a very useful concept, because we're going to talk about this in the context of scattering experiments. So, in a scattering experiment, one might take a particle and shoot it towards a stationary target. Now, to get away from a special frame of reference and make things easy and symmetrical, it's conventional to choose the center of mass frame of reference. What one does is to add a velocity to each of these particles such that the total momentum in the center of mass frame of reference is 0. The reason one does this is because momentum is conserved in collisions, gives one a very convenient frame of reference for calculating collisions with conservation of momentum. If the two particles are equal, it would then correspond to adding a half v to this particle and a half v to this particle, and so now the collision would look like this in the center of mass frame of reference. We will continue in the next module.